Okay, so this is Module 3, Multiple Regression Analysis, Analysis Variance, the General Linear Model. What is the General Linear Model? The General Linear Model is a flexible additive model. It's composed of two highly similar tools. We have ANOVA and multiple regression, which operate in many similar ways and have the same statistical principles, tests, diagnostics, and they do differ slightly in what they analyze and how they handle specific components of the linear model. I guess most specifically would be the residual or error classification of the epsilon. In terms of the equation that the model operates under, y represents the dependent variable, b naught is the coefficient for when our intercept is 0, b is the weight assigned to each predictor, x is the vector of predictors themselves, and epsilon is the residual or error, depending on the form of the general linear model being used. Regression takes into account covariates, which are continuous variables, while ANOVA only takes into factorials, which are categorical by nature. MRC also has an emphasis on testing regression parameters, while ANOVA is more focused on the specific differences between classes. The most important difference between these two is how they treat the epsilon value in the equation. In regression, it's treated as a residual or unexplained phenomena that should be analyzed to see how well data fits the model or doesn't fit the model, whereas in ANOVA, epsilon is seen as an error, which is merely just pure noise. And ANOVA also assumes that our factors are independent and unconfounded. Most of this presentation will focus on the similarities between the two, most notably on the fact they both rely on Gauss-Markov assumptions, which I'll elaborate on in the data later. And in addition, many of the hypothesis tests and diagnostic tools in one may be used with another, like I said before, with the exception of the use of f-tests and t-tests and how sum squares are used to explain variance. So here we have our data set. We have 8 factors, 7 covariates, and 4 dependent variables. And here's our regression analytics. I used x1, x2, and x3. x1, x2, and x3 respectively are fear, joy, and anger. And then we'll have y1, which in this case we'll just call emotionality. We also have our b0 intercept and all the subsequent interactions between the 3 covariates. Remarkably, I have a knack of doing this. None of the critical p-values are below 0.05, not even the intercept. So there's absolutely nothing significant here. One thing of note is that our t-values are quite low because our standard errors consistently are higher than our b-values. So that's a pretty good indicator in itself of why we fail to reject null in every single analysis here. Our R-squared results are good at showing that we're explaining a little over about a third of the variance, but however, as King mentions in the use and interpretation of R-squared, resulting R2 values can often be misleading, so comparing this value to another value and not using it as the by-all, end-all is a better way to go about interpreting data. In this case, the output here is a good example of this. So our adjusted R-squared is noticeably lower than our multiple R-square, with explained variance dropping from about a third to about a tenth, which means that at least one of the variables here is not helping improve the predictive strength of our model. Alright, so digging in further now to look for any potential type 2 errors, the first thing I wanted to do was to see if any of our predictors correlated with each other to an extent where there's any kind of instability in the model. Typically, we can get away with using scatter plots for correlation matrices when running diagnostics for multicollinearity, in a bivariate model at least. But multivariate analysis call for something a bit more heavy duty, like a variance inflation factor analysis like we're using here. So there's certainly some degree of standard error inflation going on here, although our R-squared values aren't low enough where it's not that big of an amount. Now, if any of these predictors were over 5 or so, then we'd have a serious problem. We need to remove the variable and go back and run correlation matrices of our variables against each other, or we could go back and run a regression using type 1 sums of squares and just see how things played out amongst other options. And then also I wanted to check out the rectilinearity of our 2 higher inflated covariates, x1 fear and x3 anger. I accidentally cut off the bottom heading, but the plot on the left is fear and the plot on the right is anger. In doing so, we see that both factors have nice straight lines, so the covariates are rectilinear with our dv, and our low S-curve for anger is a bit more sensitive to the disturbances on the left side of the axis. But in general, there's nothing offensive about either of these graphs, so it's safe to assume that we do have rectilinearity. So far we've seen some indications that there is some form of skewing going on in our data that might be influencing our model, so I figured it would be interesting to look at how our individual observations may be swaying our results. Cook's distance here tells us that the 3 points with the most influence in our regression line are the 11th, 28th, and 14th observations. When a single point like these has substantial influence in our model, the weights and predictions we make for all of our observations are influenced. And because these points are all good ways off the distribution line, I went back and tried to figure out the extent to which these 3 points were actually swaying things. I went with the ham-fisted approach first, and I just removed all 3 points, and then I added each back in gradually. And although our line for our standard residuals changes substantially here, I like to conserve data, and therefore I'd probably just exclude observation 14 if anything, because it does have decently large leverage and a pretty strong influence, while I feel like points 11 and 28 still fall within the range of being logically explainable. And in fact, also I ran another Cook's distance, only excluding point 14, and the resultant graph I got was nearly identical to the one on the right here. Alright, checking our model for the validity of more assumptions here. The GLM assumes that our residuals are uncorrelated and normally distributed, and running diagnostic tests for the independence of residuals such as this one can give us an easy to interpret visual indication of these assumptions. On the graph to the left, we have our y-hat values for our model plotted against our residuals, and we can see that we have a largely straight line hovering around 0 as should be expected, so everything checks out here. There's really no correlation to be found, so our residuals are independent, and you can also see that our residuals are nice and evenly distributed, with the exception of points 8, 4, and 26, but it's not enough to really make a substantial difference, and it's safe to assume that we're in line with our Gauss-Markov assumptions. Examining the normality of our residuals further, looking at the graph on the left, I first analyzed normality on a smaller scaled single predictor level. I have one of our predictors, in this case fear, plotted against its residuals to see if they are normally distributed and that there isn't any predictable relationship to be seen. We can see that our values in our graph resemble a normally distributed shape, and the sum of our residuals is essentially 0, so this checks out to me as well. And going back to making inferences about normality on a multivariate level, using a normal QQ plot, we can see that our residuals are normally distributed because they form essentially a straight line. We do see a little bit of tapering on the extreme left and right ends of the x-axis, but it's not enough. It's not a S shape or anything like that, so we don't have to be too concerned about it. QQ plot distributions like this one can also say something about the variance of our residuals, and more specifically heteroscedasticity or homoscedasticity, as we're about to see. Lastly, with MRC, I wanted to check the consistency of our variance of our residuals. So like I just said, I check for heteroscedasticity, and more specifically, I'm looking for homoscedasticity. As Cortina points out in his methods misunderstanding paper, for each set of values for each independent variable in MRC, we should have a constant variance in our errors. So that's what I was talking about in the last slide, and that all relates back to the assumption that our dependent variables are continuous. And here, what homoscedasticity would be is the consistent variance in our errors. If there's constancy in our residual values, we should see a plot that resembles a straight line. And here, our line tapers off from the far left side of the axis, similar to the one we just saw. While it's mostly a straight line and homoscedasticity isn't violated, as our fitted values increase, we do see like a notable increase in the magnitude of our residual values as we go across the x-axis. And I'd argue that it's slightly uncertain that this is the best linear, unbiased estimate for our model. If we can identify any potential predictors that are missing from the model here that could potentially explain anything, we can make better predictions and should see less of a spread in the magnitude as we go across the x-axis. So, in conclusion, for our regression analysis, our implications are as follows. We found no significant results across all factors and interactions. Like I said, I have no idea why I always pick the ones where there's nothing there. The adjusted R-square value implies that at least one factor is not adding to the predictive strength of the model. We should always look at not just the R-squared, we should look at other factors around it because R-squared itself is just a percentage. Also, as we saw multiple times, case 14 in Cook's distance has had a significant leverage and relative importance to our parameter estimate, and our results may be different if we exclude case 14. And also we have noticeable various inflation contributing to our inflated standard error, especially for x1 fear. And our residuals are both independent and normally distributed. So there's lots of good things to be seen, and there's also some questionable things and bad things to be seen. Alright, so swapping covariates for factors and moving on to ANOVA here. I took F5 and F7, which I've labeled here as depression and loneliness, And we also have the interaction between depression and loneliness as well. I ran an ANOVA against Y1, and surprise, surprise again, I found no significant results. Much of our data on the ANOVA table is either an equation of some variance or a ratio of variances. Our degrees of freedom create the parameters for our f-test and are 1 and 26 respectively here, coming from the degrees of freedom for our factors divided by the degrees of freedom for our residual. In addition, we also have our between group variances in the form of our sums of squares and mean sums of squares for depression, loneliness, and their interaction, with our mean squares coming from the sums of squares divided by degrees of freedom. Unlike our MRC, we have an f-test, which is an omnibus, which means it's a test for overall significance of the model. Because our f-test concluded that none of our factor slopes were significantly different from each other, even if one of our variables had a p-value of 0.05, it would likely not be interpreted as a significant result, which is why sometimes you see type 2 error cases in ANOVA due to overstringency. Running diagnostics for ANOVA for our y-hat values, I decided to show an example of two separate graphical representations we can use to evaluate the normality of our residual distribution. In both the QQ plot and the histogram, we can take the same conclusion, and that's that our errors are normally distributed, which is a good sign for our error variance that's consistent and random. You can see how both plots graphically handle the minor skew that occurs as we go across the x-axis, with that slightly larger cluster between 0 and 1 being present in both graphs, as well as the gap between the rest of the data and our outlier value at case 30 as well. Another point of interest I found was when running our y-hat values against our residuals to test independence, I uncovered a slightly positive relationship between our residuals and y-hats, which is concerning. Eyeballing the graph itself, you'd expect to see a negative line, if anything, based off the results, but the cluster of observations to the far right side of the x-axis are influential enough to pull our trend line away from being horizontal or slightly negative to positive. It would be optimal if our trend line was horizontal here, but due to the sensitivity of our trend line to those extreme data points, we still see this slight positive relationship. We still see an overall symmetry as well, however, so that's why our QQ plot and histogram still work out normally. Lastly, examining homoscedasticity, we can see again how the points situated in the far ends of the x-axis influence our data. And the curve line we see here is definitely the worst indicator that we have some level of heteroscedasticity, and our model might not be the best or least biased estimate for making predictions, so we're evaluating our blue rule. And then again here, with more outlier influence, we can see that case 14 is really the only outlier that's impacting things to a degree that's worth considering throwing out from our analysis. So in conclusion, for our ANOVA, we found no significant predictors or interactions between depression or loneliness on sadness, which, of course, not surprising. The independence for our residuals and, in result, our factors is questionable. And we did see sway on the two graphs on the left side of slide 12 on the extreme left end and right end of the x-axis. So that could potentially be a cause as well as case 14 in both our MRC and ANOVA had significant enough leverage to warrant possible exclusion, so that could be a contributor as well. And then also our residuals were, despite all this, normally distributed, and our error variance was constant. Here are my hand calculations, which I actually did correctly the first time around this time, and I actually checked. Alright, well, that's my presentation. I just want to thank you again for getting me into the class. Really appreciate it. And if I don't see you before the end of break, I'll definitely see you around next semester.